heads up. Say me with my lack of a head and this drum head here were to flip a coin 4 times. What's the probability that the coin would be heads up 2 out of the 4 times? You will find out today in this tutorial video. Today we're talking about topics 5.7, 1.3, and 5.8. These topics concern the expected value of a discrete random variable, the binomial theorem, and binomial distribution. What does all that stuff mean? Well, it's important that we define some key terms first. So we're talking about random variables. What even are random variables? Well, a random variable is a variable that takes on numeric values. For this, we use a capital letter. You'll see the capital letter X a lot. Now, a discrete random variable is a numeric value that is the result of a random experiment. But we'll also be dealing with binomials. What is a binomial? Well, a binomial is the sum or difference of 2 terms. Usually, for our purposes today, we'll be seeing it in an algebraic expression. And then when it comes to probability, we'll be calculating probability today of a binomial experiment. What is a binomial experiment? Well, a binomial experiment is an experiment with n trials, but there are only 2 outcomes: success or failure. When you kick a soccer ball, it goes in the goal or misses. Those are the only 2 options. For calculating the binomial expansions and the probabilities in binomial experiments, we use the binomial coefficient. This as n choose r. N is the number of trials, r is the term you're looking for. So you get that if you look in your formula booklet under topic 1.3, you see that it comes from n factorial over r factorial times n minus r factorial. Factorial is a number multiplied by its preceding real numbers. I mentioned that we'll be talking about probabilities and probability distribution. So what is probability distribution? Probability distribution is usually seen in a table that has all the values of a random variable and their associated probabilities. If we go back to the soccer example, a probability distribution, or a binomial probability distribution in this case, would be a table that shows the probability of 1 success, so 1 ball in the goal, or 2 successes, 3 successes, 3 balls in the goal, and so on. The last term we need to cover is expected value. So the expected value in our binomial distribution or binomial experiment is the mean, the average, of the probabilities. So that means the sum of the random variable, so say in our soccer analogy, 2 goals, 2 successes, it's going to be 2 times the probability of 2, and then you add that plus 3 times the probability of 3, etc. Now it's time to move on to a problem. Let's look at some probability distribution, shall we? This problem says, Andy, when he performs a saxophone solo, plays a particular note correctly 61% of the time. If Andy plays the solo 12 times, what is the probability that he will play the note incorrectly 7 of those times? So this is binomial distribution. So there's a success and a failure. In this instance, the success is that Andy plays the note in the solo correctly. The failure would be if he plays it incorrectly. So that means we have 7 failures. So if we look at that, we're going to do probability of big X. Remember, big X is a random variable, so not discrete. The discrete random variable is going to be 7 because 7 is the result of a random experiment, being Andy playing his saxophone solo. Big X is just a random variable because it takes on a numeric value regardless of the experiment. Anyway, if you look in your formula booklet at topic 5.8, you will see a binomial distribution formula. So we'll be using that because we're looking for 7 failures. So big probability of X equals 7. That makes sense. Here comes that binomial coefficient again. Remember, so it's n choose r. N is the number of trials. How many trials do we have here? 12. So that's n is 12 choose r is the term we're looking for, so 7. And then next in your formula book, you get p to the r. P is probability. So don't let this trip you up here. Probability here does not mean probability of success. It means probability of failure. So if our probability of success is 61%, that means probability of failure is 39%. So that's what we're going to put here. We're going to put 0.39, 39% in decimal form, to the r power, r being 7. Next, we have the probability of success. That's going to be 1 minus p, what we already have, so that's 61.61. And that's to the n minus r power. So 12 minus 7 is 5. You work that out, we're going to have our answer. We're going to have the probability of Andy failing 7 times out of 12 attempts. So let's work this out, shall we? So first, let's do the binomial coefficient. We have 12 choose 7. So that's, if you remember from your formula booklet, go back to topic 1.3. You have 12 factorial, because it's n, over 7 factorial times 12 minus 7 factorial. So when you work that out, you get 792. And then let's just work these out, these exponents. So we got 0.39 to the 7th power. If you take out your calculator, you'll find that it's a pretty small number. It's 0.00013723101. I'm writing it down so you can see it. You're going to want to store that in your calculator. Then 0.61 to the 5th power. When you calculate that out with your calculator, you get 0.0844596301. So we've got 792 times 0.0013723101 times 0.0844596301 equals the probability of x equals 7. So remember, this probability that he plays the note incorrectly 7 times out of 12. You work that all out, you calculate this, you get to that probability is 0.092. You can also express as, with decimal 2 places, 9.2%. Alright, now we're on to problem number 2. This one extends the previous problem by a different way. This problem says, if Andy plays the solo twice, make a table showing the distribution of the probability that he plays it correctly. So this is binomial distribution. This is a binomial distribution table. So keep in mind, a very important thing to note here is that he's playing it twice this time instead of 12 times. So that's a little simpler for us when we're making a table. So if you remember how we found 7 out of 12, we're going to have to do that for each one of these values here. We're going to have to do it for probability that but now we're looking at correct, so successes. So the probability of success is 0.61 or 61%, not 0.39, which is the probability that he'll play it incorrectly. So let's get to work. We'll have to find the probability in the same way we did 7 out of 12, or 12 choose 7, 2 choose 0, 2 choose 1, and 2 choose 2. So let's start with this one, shall we? Probability of big X equals 0. It's the random variable. Equals 2 choose 0 times 0.61. Remember, probability of success 2 to the power of r, so that's 0, and then 0.39 squared. This one's pretty simple, because a rule of thumb is that any choose 0, so any n choose 0 is always 1. So we know that right away. That's pretty simple. And then you will also remember from your laws of exponents that any term to the 0 power is also 1. So that makes it pretty easy for us. And then we just have 0.39 squared, which if you put that into your calculator is 0.1521. So probability of x equals 0 is 0.1521. That's an exact value. Otherwise, 3 significant figures. So that goes right here. Alright, now that we have the probability that Andy will play the solo correctly 0 times out of 2, now let's move on to 1. So, as you might expect, it's probability of x equals 1. So, we're going to do 2 choose 1. Remember, n over r, number of trials over term we're looking for. So, that's 2 over 1. And then, remember, probability of success, that's 0.61 to the r power, which is 1. And then probability of failure, which is 0.39. And then that's also to the 1, because that's n minus r. N minus r is 2 minus 1. 2 minus 1 is 1. So if you work out the binomial coefficient, which you'll remember is n factorial over r factorial times n minus r factorial, so it's 2 factorial over 1 factorial times 2 minus 1, which we know is 1, so 1 factorial. And 1 factorial is 1, so that's 1 times 1. And then 2 factorial is 2, because it's 2 times 1. So that's just 2. So that's pretty simple. We got 2 there. And then 0.61 to the first power is just 0.61. And then 0.39 to the first power, just 0.39. So when we multiply that all together, we get probability of x equals 1 equals 0.4758. Alright, we have the first two. We have the probability that out of 2 tries, Andy plays the solo correctly 0 times, and then Andy plays it correctly once. So we got one left. That's probability of x equals 2. So if we look back at our binomial distribution formula, see that it's just 2 choose 2, remember? 2 trials, and then we're looking for 2. And then probability of success, that's 0.61. and then to the r power, r is 2, so squared, and then 0.39, the probability of failure, to 0, because 2 minus 2, that's n minus r, is 0. So if you work out the binomial coefficient, as we've been doing first, you get 2 factorial over 2 factorial times 0 factorial, because 2 minus 2 is 0, of course. Important thing to know is 0 factorial is 1. So you get 1 times 2, because 2 factorial is just 2, because 2 times 1. So 1 times 2 is 2. 2 divided by 2 is 1. So our binomial coefficient is just 1 again. So 1. And then if you work out 0.61 squared, that's 0.3721. And then 0.39 is to the 0 power. And as we know from our laws of exponents, anything to the 0 power is just 1. So 0.3721 is the probability that of both times Andy plays the solo, he does it correctly. So we have our binomial distribution table filled, and now this problem is asking us to find the expected value of this table's big X. So if you'll remember, the expected value is just the mean of the probability distribution, and that means it's just going to be little x times this times the probability of big X equals little x. So 1 is going to be 0 times 0.1521 plus the next one, and then the next one. So this is going to be not too difficult for us here. And we annotate expected value of x as such, e of x. So remember, we're going to do 0 times that. 0 times 0.1521 plus 1 times 0.4758, and then plus 2 times 0.3721. So 0 times that, 0 times anything is 0. So we don't have to worry about that. And then 1 times this is just that. So just 0.4758 plus 2 times 0.3721, which if you put that in your calculator, you get 0.7442. Add those together, and you get the expected value of this probability distribution of big X is 1.22. So for this last problem, we're past Andy. Now we're on to binomial expansion, no longer binomial probability distribution. So for this problem is asking us to find the coefficient of x to the 4th term in the expansion of 3 times x plus 3 to the 15th power. So this process is actually going to be pretty similar to that of the previous problems. It's a similar formula. If you look at your formula booklet at topic 1.3, you'll see the binomial theorem. So the x to the 4th term. What does that mean? Well, the terms in this binomial expansion are going to go like this. We're going to descend. If we got 15 terms, we're going to go 15, 14, 13, 12, and so on. So we're going to have to get to 4. When you count it out, the first one is 0, the second one's 2, etc. When you get to 4, 4 is the 11th term. So if you look at your binomial theorem, it's what we have here, 3 times x plus 3 to the 15 equals the binomial coefficient, which is n over r. What's n again? Well, n in this instance is not the number of trials, but the number of terms. So that's going to be 15. And then r is, of course, the term we're looking for, which is going to be the 11th term. So that's 11. And then it's going to be that times a. This is a and b. X is a, 3 is b. So it's going to be a to the n minus r power. So that's going to be x to 15 minus 11 is 4. X to the 4th power. There it is. It's already there. We just have to calculate this all out. And then it's going to be 3, which is b, to the r power, which is 11. So there you go. And we're just going to calculate this out. So first we got the binomial coefficient, of course. 15 factorial over 11 factorial times 15 minus 11 factorial. So it's going to be 4 factorial. When you work that out, you get 1,365. So that goes right here. 1,365. And then just x to the 4th. And then 3 to the 11th. If you put 3 to the 11th power in your calculator, you get 177,147. So that looks like this. Times x to the 4th. This stays over here. Sorry about that. And that equals this. So work that out. 1,365 times 177,147, and you get 2, 4, 1, 8, 0, 5, 6, 5, 5, x to the 4th. But wait, that's not all. As you can see, 3 in this is a coefficient for the whole expansion. So we have to multiply this by 3 because it's right there. After we do all this, this big old number is just the coefficient within x plus 3 to the 15th. But now we gotta multiply it by 3 because 3 is multiplying every term. So because it's gonna be such a humongously large number, I'm just gonna keep it as that big old number times 3 times the x4th, and that's the coefficient. So there you go. The coefficient is 241805655 times 3 of the expansion of 3 times x plus 3 to the 15th. That's it for this video, but I'll assign you 2 IB style questions to do. I'll put the images of those and then the answers following this. Thanks for watching.